let's recall some facts about limits and continuous functions from single variable calculus. For example, we defined a function f of x to be continuous at the point x equals a if the limit as x goes to a of f of x is equal to f of a. So not only do we need the limit as x goes to a of f of x to exist, but for that function to be continuous, that limit must equal f evaluated at the point x equals a. Examples, let's look at a few functions and determine whether the limit as x goes to a of f of x exists and whether the function is continuous at x equals a. So let's start with f of x equals x cubed minus x plus 1. And let's look at the limit as x goes to 0. So there are a few approaches that we can do. We can view what happens as we approach x equals 1 from the left, and what happens as we approach x equals 0, from the right. And we notice that as we approach from the left and we approach from the right, they approach the same point. And so that gives us an indication that the limit exists. Now the limit as x goes to 0 of f of x, visually we see that that is 1, and that is indeed f of 0. And so algebraically, just by substituting in the point x equals 0, we can see that the limit as x goes to 0 of f of x is 1, which is f of 0, and indeed then the function is continuous. Let's look at another example. F of x here is defined to be x cubed minus x plus 1 when x is less than 0, and then x squared minus 1 when x is greater than or equal to 0. So if we approach this limit from the left, we'll get a value of 1. But if we approach this limit from the right, we'll get a value of negative 1. And so the limit as x goes to 0 from the negative side of f of x is 1, but the limit as x goes to 0 from the right, from the positive side of f of x, is negative 1. These left-hand and right-hand limits are not equal, so we see that the limit does not exist. Well, if the limit does not exist, then at that point the function cannot be continuous. And we have this intuitive idea of continuous functions not having any sort of break or jump. And so here you can see that the function jumps between 1 and then negative 1 at x equals 0. Finally, let's look at the function f of x equals x squared minus 1 over x minus 1. Now, if I approach this limit from the left or the right, approaching the limit as x goes to 1, then you'll notice that the limit indeed does exist. In fact, we can do the limit as x approaches 1, and we can think about x squared minus 1 as being x minus 1 times x plus 1 over x minus 1. And then the x minus 1's then cancel, and so we get a limit of 2. So the limit exists and it equals 2. But the function does not exist at x equals 1. Okay, so here, this function does not exist at x equals 1. And so, although the limit does exist, the limit does not equal f of 1, because f of 1 does not exist, and so this function is not continuous. And so this gives us some ideas of the types of things that can happen with limits, and whether they exist or not, and whether the function is continuous or not at a point. So let's brainstorm and think of some criteria for determining whether a limit does or does not exist in single variable calculus. One thing that we checked is that we had to verify the left hand and right hand limits were equal. Okay, that was a way that we could determine whether or not a limit existed. Okay, we could also possibly simplify the expression and evaluate at the point. And that would tell us whether the limit did or did not exist. So we want to apply some of these principles then to limits of multivariable functions. So let's look at a simple definition for a multivariable limit. The function f of xy approaches a limit L as xy approaches the point x0, y0 if we can make the values of f of xy arbitrarily close to L by making xy sufficiently close to x0, y0. So what we're trying to say is that if you were to give some sort of cutoff of how close f of xy needed to be to the limit exists if I can make the point xy close enough to the point x0, y0 so that f of xy is indeed close to L. And this is the same notion of limits that we had from single variable calculus. Now, what about continuity? How does that work? Well, the function f of xy is continuous at xy equals x0, y0 if the limit as xy goes to x0, y0 of f of xy is equal to f of x0, y0. So this is actually the same definition of continuity that we had for single variable calculus. We need the limit as x and y goes to x0, y0 to exist, and we need it to equal f of x0, y0 if our function is going to be continuous. Now we want to explore a couple more examples where a limit may or may not exist. Okay, so our first example is going to be, let's find the limit as xy goes to 0, 0 of x squared minus y squared over x plus y. And the first thing I want to point out is that if I was to just substitute in the point 0, 0, then I would get 0 in the numerator and 0 in the denominator, and I would not be able to tell whether that limit existed or not. Okay, so what I'm going to do is I'm going to try to find this limit by algebraically simplifying the expression. So I'm going to take the limit as xy goes to 0, 0, and then I'm going to factor the numerator. So I'm going to factor it into x plus y times x minus y over x plus y. Well, that's just the limit as x and y goes to 0, 0 of just x minus y. So here we see that the x plus y's cancel. Well, this expression, if I choose to plug in 0, 0, I'm just going to get 0 minus 0. And so the limit does indeed exist, and it is 0. And so that gives us one principle for finding limits of multivariable functions, and that is to try to somehow simplify the expression and then substitute in the point. And if we're able to do that, then the limit does exist. Now, let's look at an example where the limit does not exist. And the way that we're going to show that a particular limit does not exist is we want to use the same concept as we had in single variable calculus, which was to approach from the left and approach from the right. Except for in multivariable calculus, as we approach a particular point, we can approach it not just from the left or the right, but we can in fact approach it from any direction. And so what we need to do is to see what happens when we approach this limiting point from any direction. So what we're going to do is we're going to pick particular paths. Okay, we're going to parameterize various paths and let those paths approach our limiting point. Okay, so for example, if I want to find limits that go to 0, 0, I might let x be t and y be 0. Or I might let x be 0 and y be t. Or I might let both x and y equal t. The idea here is that if I'm trying to approach the point 0, 0, I can approach from this direction along the curve t0. I can approach from this direction along the curve 0t, or in fact, I can even approach from this direction along the curve tt. In each case, I would be looking at a limit as t goes to 0. Okay, so we're going to show that the limit of x squared over x squared plus y squared as xy goes to 0, 0 does not exist. Okay, so I'm going to consider some paths. So I'm going to let x be t, and I'm going to let y be 0. And I'm going to approach along that path. I'm going to take the limit as t goes to 0, then of x is t, so that's t squared, over t squared plus 0 squared. And that in fact is going to be the limit as t goes to 0 of 1, which is 1. Okay, so we might think that the limit is 1, but what if we let x be 0 and then y equal to t? So now we're approaching from above. We're going to let the limit as t goes to 0 of 0 over 0 squared plus t squared. Since we have a 0 in the numerator, that's just going to be the limit as t goes to 0 of 0. And that is in fact 0. Well, that is interesting then. So if we approach, okay, again, let me just move this. If we approach from the left, then we get a limit of 1. But if we approach from above, then, sorry, if we approach from the right, we get a limit of 1. If we approach from above, we get a limit of 0. Now, that means that the limit doesn't exist because as we approached from either above or the right, we saw that that the two limits were not equal, and so therefore the limit does not exist. If we should be able to approach from any path, approach that point 0, 0 from any path in order and have it be equal in order for the limit to exist. But I don't want you to just restrict yourselves to these two paths. We want to be able to go from any direction. And so even though we showed the limit doesn't exist just by using those two paths, I'm going to throw in a third path, which actually gives you a different result. Because sometimes you will need to do this path when x is t and y is t. So if we do the limit as t goes to 0 in that case, we would get t squared over t squared plus t squared. And that is going to be the limit as t goes to 0 of t squared over 2t squared. Those t squareds are going to cancel for me. And so, in fact, that limit is going to be 1/2. And so I get a different value approaching along that line than I did from approaching above or from the right. I could even pick more paths, and we should be aware of that. We could pick paths that were like a parabola, for example. You could pick x equals t and then y equals t squared. That's another kind of path that you could pick to show that maybe a limit does not exist. What's great about this method of picking different paths is that it will show that a limit does not exist when you get different limits approaching from different paths. But this method has a flaw in that you cannot show that a limit exists in this way. To show a limit exists, you would have to either simplify the function first, like we've done here, or if you follow this activity to the end, you can change the coordinates, say, of a function that's on a two-dimensional domain. You can change the coordinate system to something like polar coordinates, and then you'll be able to approach the point 0, 0 or another point from all directions. And so sometimes a coordinate change is a nice way to show that a limit exists.